আমার প্রিয় শিক্ষার্থীবৃন্দ, সহকর্মীবৃন্দ এবং যে সকল দর্শক এই মুহূর্তে ফেসবুক লাইভ এবং ইউটিউব লাইভের মাধ্যমে আমাদের এই প্রোগ্রামটি দেখছেন, আপনাদের সকলকে আমাদের ফেসবুক পেজ এবং ইউটিউব চ্যানেলে স্বাগতম। আশা করি সকলে ভালো আছেন এবং সুস্থ আছেন। শুভ সন্ধ্যা সবাইকে। আপনারা ইতিমধ্যে অবগত হয়েছেন যে আমরা এই বিশ্ব করোনা মহামারীর সময়ে আমরা পদার্থবিজ্ঞান বিভাগ, পাবনা বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয় পদার্থবিজ্ঞানকে আকর্ষণীয় করে তোলা এবং আমাদের ছাত্রছাত্রীদেরকে পড়াশোনায় ধরে রাখার জন্য আমরা একটা উদ্যোগ গ্রহণ করেছি। আমরা ইন্টারন্যাশনাল ফিজিক্স ওয়েবিনার আয়োজন করে যাচ্ছি। ইতিমধ্যে আপনাদের সহযোগিতায় আমরা 92টা ইন্টারন্যাশনাল ওয়েবিনার সফলতার সহিত আমরা আয়োজন করতে সক্ষম হয়েছি। আজকে আমাদের 93তম আমাদের ইন্টারন্যাশনাল ফিজিক্স ওয়েবিনার। তো আপনাদের সকলকে ধন্যবাদ যারা আমাকে প্রত্যক্ষ এবং পরোক্ষভাবে এই আয়োজনে সহযোগিতা করে যাচ্ছেন। তো আজকে আমাদের যে ওয়েবিনার আপনারা ইতিমধ্যে অবগত হয়েছেন, তার টাইটেলটা হলো ফ্যাসেটস অফ কন্টেম্পোরারি অ্যাটমিক কলিশন ফিজিক্স ইন্টারডিসিপ্লিনারি সায়েন্স, এবং আমাদের স্পিকার হিসেবে যিনি আছেন তিনি হলো আমাদের শ্রদ্ধেয় স্যার ডক্টর লোকেশ সি ত্রিবেদী স্যার সিনিয়র প্রফেসর ডিপার্টমেন্ট অফ নিউক্লিয়ার অ্যাটমিক ফিজিক্স, টাটা ইনস্টিটিউট অফ ফান্ডামেন্টাল রিসার্চ, TIFR, মুম্বাই, ইন্ডিয়া। এবং স্যার ইতিমধ্যে আমাদের সাথে সংযুক্ত হয়েছে। স্যারকে আমি আমাদের ওয়েবিনার এবং আমাদের বিশ্ববিদ্যালয়ে স্বাগতম জানাচ্ছি। স্যার নমস্কার, আপনাকে অনলাইনের মাধ্যমে আমাদের ওয়েবিনার এবং বিশ্ববিদ্যালয়ে স্বাগতম এবং অনেক অনেক ধন্যবাদ। এই প্যান্ডেমিক সিচুয়েশনে আমরা যে উদ্যোগটা গ্রহণ করেছি সেই উদ্যোগে আমাদের অনুরোধে আপনি সাড়া দেওয়ার জন্য এবং তার জন্য আমাদের বিভাগের পক্ষ থেকে আপনাকে ধন্যবাদ এবং কৃতজ্ঞতা প্রকাশ করছি স্যার।
নিশ্চয়ই, থ্যাংক ইউ।
এবং আমরা যে উদ্দেশ্য নিয়ে স্যার এই যাত্রাটা শুরু করেছিলাম সেটা হলো আমাদের আপনি অবশ্যই জানেন যে প্যান্ডেমিকের সময় আমাদের ইনস্টিটিউশনগুলো যখন বন্ধ, এখনো বন্ধ আছে আমাদের। প্রথম দিকে আমরা যখন লকডাউনে ছিলাম তখন ফ্রাস্ট্রেশনে চলে যাচ্ছিলাম আমরা, ইভেন শিক্ষকরাও। তখন ভাবছিলাম যে একটা কিছু করতে হবে আমাদের ছাত্রছাত্রীদেরকে এই ফ্রাস্ট্রেশন থেকে বের করে আনার জন্য। তখন আমরা একটা চিন্তা করলাম যে অনলাইন ক্লাসের পাশাপাশি যদি বিশ্ববিখ্যাত যারা পদার্থবিদ আছে তাদেরকে নিয়ে যদি এরকম ওয়েবিনার আয়োজন করা যায়। তো আমরা একটা দুটো করতে করতে আজকে আমাদের 93তম ওয়েবিনার। তো আসলে আপনাদের সকলকে ধন্যবাদ। আপনাদের মতো বিজ্ঞানীরা আমাদেরকে সহযোগিতা না করলে তো হয়তো আমরা এভাবে এতগুলো ওয়েবিনার করতে পারতাম না। তো স্যার অনেক কৃতজ্ঞতা। আপনার স্যার এখন শুরু করতে পারি, এটা আপনার সময় স্যার।
Okay, so can you hear me?
Yes sir, we can hear.
Okay, very good. Thank you very much for very kind introduction, and very nice that you have been organizing this webinar series for a long time. এটা খুবই ভালো উদ্যোগ, so I think we need to support. And এটা এমন কিছু প্রবলেমই নয় আমাদের পক্ষে to give a seminar, at least for me, কারণ এখন তো আর কোথাও ট্রাভেল করে যেতে হচ্ছে না, so we are in home or we are in the office, so right now, so it is not a problem for giving a seminar. You don't have to take a flight, you don't have to book a flight, you don't have to get a funding or somewhere, so it is easy. However, we look forward to physically meet in near future. So I will
সেই দিনটার জন্য অপেক্ষা করব স্যার অবশ্যই।
Yes, right. I have never come to Bangladesh, although my home is very close to Bangladesh. I'll show you some of the pictures. Okay, so let me start my talk, and I'm assuming the audience has perhaps have many students, and if that is the situation, I'm assuming that nobody is expert in this field. So therefore, I'd like to explain things, whatever I am planning to talk, and typically, as you said, 1 hour, 10-15 minutes, it should be over, and even between some question comes, I'm ready to take any questions. Particularly for the students, if you do not understand, don't hesitate, just ask or write, whatever the way Pretam is organizing. Okay, so the talk of the today's topic, the title is Facets of Contemporary Atomic Collision Physics, Interdisciplinary Science. So I'll explain what it means. And okay, this is a picture, I come from Tata Institute of Fundamental Research, TIFR. As many of you know the name of this institute. It is right on the Arabian Sea, in the west part of India, and where I am here for many, many years, although I originally happens to be from West Bengal. Now, here, this is the Arabian Sea, and this is a little bit of a distance. If it's a very nice view, if one could go to seashore and look at the little bit of a distance, you can have a very, very nice view of the city, part of the city. So let me not go into the details of this. So just here, just coming back right on the topic, Of course, don't get frightened. এগুলো দেখে অত ভয় পাওয়ার কিছু নেই। অনেক ধরনের atoms এবং molecules আমরা study করি over many years. It is not just 2 years or 5 years. Over many years, we have been studying this, and as a result, you could, get into some kind of idea, some kind of topic, some kind of theme. So, for example, this I will be talking a little bit later. This is called interference topic. I hope my cursor is visible. So one thing is the very simple atoms like hydrogen, atomic hydrogen, or this is molecular hydrogen, or helium, or neon. These are the simple atoms or molecules. But life is not always that simple. Life has to deal with a lot of complicated affairs, complicated molecules too at the same time. So simple atomer ক্ষেত্রে আমরা যে সমস্ত কোশ্চেন গুলো ask fundamental physics questions, how does an independent particle behavior works? Of course, we know atoms and we know molecules, but day by day the research is asking deeper questions. So whatever today's research will come to text maybe tomorrow, maybe 10 years later or even later, but people have to ask questions, and that is why keeps us alive in the research. For example, independent particle behavior, correlation, electron correlation is a very major topic, not only atomic molecular physics, but condensed matter physics or many other physics, even nuclear physics, where correlation topics keeps on coming. Interference, basic collision models. So these are the questions one asks for simple atoms and molecules. But you can go a little beyond simple atoms and molecules. For example, go to nitrogen. Go to oxygen, it has many more electrons than hydrogen, or go to methane, or now go to little bit complicated molecule, water. So we are growing complications slowly and increasing the complications and creating more complications for our lives, for experimentalists as well as for theorists. Because as you know, in a simple atom is very easy to deal sometimes. For a hydrogen atom, for example, if you have analytical wave function. But the moment you go to 2-electron system like helium, life becomes complicated. You have to have some approximation to write down even the wave functions. It's not easy. So even a theoretical physicist who calculates many of these outcomes or results, what we do from experiments, they always try to do many approximations based on what atoms, what molecules, what are the number of electrons, and many other parameters. I'll come to that slowly, like collision parameters. But here, I am increasing the difficulties by increasing the number of atoms, molecules, as well as number of electrons. For example, H2O is a little more complicated. Similarly, you keep on increasing. For example, next you go to uracil. You may ask me a question, why do I talk about uracil? C4H4N2O2. This is like here uracil molecule. I'll come to this little more details. Or adenine. These are the building blocks of, these are part of the DNA, RNA based molecules, okay, nucleobases. And there are a lot of applications for this. Similarly, I have another round here, another ellipse in which I have shown, for example, C60 Fullerene. It's a large molecule. It's a kind of, people also talk about this molecule is like a carbon cluster. Okay, 720 MeV is the mass because it has 60 carbon atoms. 60 carbon atoms. It was discovered around 1986 or so. And this is another kind of molecule. It's called coronine, C24H12. Now you may ask me a question, why particularly I choose certain molecules and not certain? You see this red ellipse in which all these molecules have a common property, certain things, because they are all biomolecules, including water, because water is very important for biological applications for human body or for any living animals and their physiological aspects. For example, other circle or ellipse, you see these molecules I have chosen because they show a collective property. They have a common property. They behave collectively. The electrons behave collectively. They respond to the external field collectively. I'll come to this again. Even if you don't understand everything what I'm saying now, I'll come back later. Now you see between the two, there is one common. This is called iodouracil. This is a uracil, but it has an iodine attached with that. So this is called iodouracil, and this has both biomolecular properties because it's uracil, and we have just put iodine there. And here it's also part of a giant resonance. It shows like a collective behavior. So it's a common between the two. So that is why kind of my goal of study. But I will give you a glimpse of certain examples today. Of course, I cannot say everything today. But here are two recent review articles. One is World Scientific, which was published last year, Singapore. And another is Ecr International Conference of Physics of Electronic Atomic Collisions. It's a 60 years of Ecr, and we had published a roadmap article. I happen to be part of the international committee of this body, and I was asked to write a roadmap article along with several others. So this gives a roadmap for next generations of atomic collision physics worldwide is going to come. We are trying to put some directions there. So this will give you a glimpse of review of certain things which I am going to talk. Now, for example, if you want to do a good science, I am an experimentalist. We do a lot of experiments, equipments, and we build equipments. We build our labs. We don't depend on only things which have to be bought. We build our own instruments, and we have a fantastic workshop here and groups, scientific groups. We make our own equipments and detectors or accelerators or beam lines and so on. I'll give some examples. However, you need a theorist who can explain your data and who can help us which direction to think. So it's a combination of experimentalist and theorist. দুজনে একসাথে তবেই সায়েন্সটা প্রোগ্রেসটা ভালো হবে. So here it is. But where do I get a scientist? Where do I get a theorist? কোথায় পাবো তারে? Here is one example. Don't worry about who is this, but one is experimentalist, one is theorist. This is somewhere in UK, Belfast. We have taken this one. And if you don't want to go to that far, if you want to know, I want to go to a great, wall of China, it's okay, you are there also. You will not miss some experimentalists or theorists. So whenever we go conferences across the world, many places, we meet people, meet our colleagues, meet our friends, we discuss about the physics and what science can be done. And that's how we plan our experiments and we get going. Now, question is that this is not only limited to UK, Belfast, or Great Walls of China, even going all over the world, many conferences, many places. Only thing I realized that ghar hote shudhu dui pa felia. Okay, so this is my place, Kalyani, and this is Pabna. Actually, it is something like 200 kilometers or so. It's not too far, but this is the first time. Actually, they are giving a talk for my closest people in near my state. মানে ঘর হতে শুধু দুই পা ফেলিয়া তাই মনে পড়ে গেল আর কি. So and this is also I come from a place like this. ওই জায়গাটি যাচ্ছে দেখা এরি ক্ষেতের আড়ে ছোটবেলায় পড়া. And this place, and we are very close. So I'm sure someday we'll meet in universities close by, just going by a train or bus sometimes. So building block of materials. Just wanted to tell you that this, of course, everybody knows, but just as a preamble, as you know very well, the matter, if you breaks, you go into atoms. Atoms, if you breaks, you can get electrons and nucleus. Again, nucleus, if you break, you get protons and a neutron, and which you break, you get finally quarks. That's you need higher and higher energy if you go this way. So these are the quarks where you really do particle physics issues and problems nowadays. Then, of course, atoms are very tiny. How tiny it is? Roughly 1 lakh times smaller than our, just a hair of your, okay. And this, if you take a hair and if you, very, very small, it is then 1 lakh times smaller than that. That's the atomic dimensions are typically about angstrom. All of you know, but just to remind you, now to probe these atoms and molecules, you need to go inside. How do I go inside? Can I go inside atoms? Suppose you have a honeycomb. Can a human being, however intelligent he is, can go inside? We cannot go. So only a honey can go there. Honey, bee can go there to pick up the honey. So honeybee or ants or some smaller objects, they only can move there. Okay, so that's the idea for the probes of similar dimensions. So that's the size. The question of size comes. Size. মানে প্রত্যেকের একটা সাইজ আছে এবং ঠিক মতো সাইজের প্রোব দরকার, তাহলে অ্যাটমস বা মলিকুলস বা যে কোনো jiniske we can examine whatever we can do. For example, if you take a brick, I can throw, maybe you can break a tree, or you can bang a door and window. But if you want to go for atoms and molecules, I need probes like ions, electrons, or photons, which can penetrate inside. And it should have energy. Suppose you take apple and you just put a bullet, just put it there, it will not go through unless you give it energy. So when you fire, then it will go through. Okay, so you need energy. So you not only probes, ions, electrons, and photons, but you need sufficient certain energy. So that's the question of energy comes. So I'll be talking about KeV energy and MeV energy collisions today. So one is example for those who are not very familiar with positive ions, which I'll be talking later. Now here is a definition of ion. One electron is moved out from this particular atom. Now which atom is this? You can easily count. So it's a 10 electrons are there, outside. So that means 10 protons are there inside. So it's a neon atom. Okay. And if I remove one electron, then it becomes positive ion of charge 1 plus. But I can remove 2 electrons also. So I can remove 2 electrons, then I can positive ion of 2 plus. So 1 plus, 2 plus, 3 plus, 4 plus, up to 10 plus possible. That means I can remove all 10 electrons in an accelerator. And for atomic and molecular physics, it is very important what is the charge state. Like I am saying neon, if I remove all 10 electrons, it's called 10 plus. So charge state is 10 plus. That means it has enough strength for Coulomb interactions. Because Coulomb force Q1, Q2 by R square, right? Divide. Similarly, in electron and ion, there's a negative sign and Q by R square because electron has one charge. So the Q is the charge state of this particular ion, and electron is suppose somewhere else. It is interacting with this Coulomb interaction, and the strength depends on the charge state Q. That is why in a nuclear physics, people do not worry so much about charge state here, because they are only concerned about the nucleus inside. Or atomic and molecular physics, not only nuclear charge, it is also important for us what is electronic charge state outside. So for example, uranium, we can go up to 92 plus. So that's why we need highly charged ions. So many of the collisions, we use highly charged ions to increase the interaction strength, the interaction potential. So highly charged ions is everywhere, all over the universe. Talk about plasma physics, material science, X-ray astrophysics, ion source physics. Everywhere you talk about highly charged ions. Of course, atomic physics and molecular physics is there. Even biophysics. Application-wise, medicine like cancer therapy or surface science, radiation biology. Some of the examples I'll give you today: X-ray projection microscopy, fragmentations of biomolecules. Okay, there are many. I will give you certain examples today based on the time. But at the same time, as I said, I'll go slowly. So I have nothing, no hurry. I don't have to catch a train. But at the same time, I don't have to pump too much of information, and I don't have to take long time either. So just to give a glimpse of the subject. What is the idea? Just see, there is a nice news in January this year. This is still 2020. Among the big news was going, debate was going on throughout India, all newspapers and televisions everywhere. Like debate is something in LS for certain bills and so on. But below that, there's more. For me, more important news is very important news is CT is set to get high-tech proton machine for safer cancer therapy. This is more important to me because that is the time in Bombay, some big hospitals are about to get proton machines, high-energy proton machines for cancer therapy. Now, what is the basics? What is the basic physics here? Okay, and do you understand all the basic physics? How proton therapy works? So that's why here, I am very impressed that these newspapers give very nice report, more precise and less harmful by using a charged particle like proton on carbon used for cancer therapy of brain or in the eyes or somewhere in the body. I'll come to this little later. So this is just a warm-up slides for all of you. So, you should have some warm up. If you are going to make it চা বানাতে গেলে চা তো গরম চা না হওয়া পর্যন্ত ঠান্ডা চায়ে চা চিনি মিশিয়ে দিলে তো সেভাবে চলবে না, টেস্ট হবে না। তো চাটাকে একটু গরম করতে হবে, ফোটাতে হবে। So I am just trying to warm up this topic so that you get to the problem. What is the problem and how do you deal with it? But as I said, many places, if you go somewhere, if you want to fight something in society or in real life, people say, banduk hai, do you have the weapons to fight? If you're just saying fight is not enough, do you have enough weapons? Similarly, I want to tackle a physics problem. Do I have accelerator? Yes. As I saw the first picture, there was accelerator. Maybe I should go back and show you. I did not explain that time much. Yes, this one is this tall tower, is not a water tank. It's an accelerator. It's a electron accelerator, so-called high energy accelerator. It can produce beam of 20 MeV to 100 MeV roughly, MeV energy, and any highly charged ions, as I explained before. Now, this is one big accelerator. Then to complement this high energy accelerator, we built ourselves another low energy laboratory which contains another accelerator. And here I am. So this is called Ecr Iron Accelerator. This is in-house. Most of the things are built by us in-house. Certain things, of course, you have to get from outside, certain things from here. But overall lab, we are the in charge, and me and my team, my group members, my students, my technical staff, we have been very involved for making this last several years. And we produce highly charged ions like oxygen 8+, argon, helium like argon, or even xenon near 30+. We can produce, and many other ions. I have not given all the list here. So this is what you are seeing is a high voltage deck. This can go 400 kilovolt. That means 4 lakhs of volts we can apply here. And we have a plasma chamber inside. This is called electron cyclotron resonance, ECR, ion accelerator. And this ECR is a plasma-based ion source. And once the plasma is there by some microwave, 14.5 gigahertz microwave, we pump on this and raise the whole thing on 400 kilovolt. So ions which are produced in the plasma. If you have any questions, you can ask me at the end. I can explain better. So these ions are accelerated and they bend through this big magnet, what you are seeing here, and through this accelerator side. And what we do here, we bend and we select the particular charge state. So instead of going details, this is the entire deck, high voltage deck, what is there inside. So we spend really a lot of time to build. And once we build, not only we use, but we give beam time like free to anybody, whoever asks, like Mumbai University, Saha Institute, Calcutta, IIST, Trivandrum, ICT, Mumbai, Guru Nanak University, Punjab University, VCC, Calcutta, Kanpur IIT, and many places. Okay, and NISAR, Bhubaneswar, BARC people. So we give many colleagues, and if anybody has interest, you can send me an email. If you have a lot of people do material science, just for ion implantation, or bioscience, or even low energy nuclear physics. It's called astronuclear physics. So astrophysics, interesting nuclear physics, which has a lot of overlap with astrophysics, and some of our colleagues are doing that. Apart from my main users, of course, I am the main users, and my group, we are using atomic and molecular physics. Here is a nice view of 3 different beam lines. We have this accelerator, as I say, this is the ion source, main plasma source. Ions are produced, that bent by a magnet. If there is a magnetic field, and if you put a charged particle, it bends. That you know from your basic physics. So here is the magnetic spectrometer, basically, through the magnet, and we select a particular charge state from here, and that particular charge state is taken through the beam line. Then there is another big magnet, and we shine the beam in any one of the beam lines. And we have electron spectrometer here, we have a recoil ion momentum spectrometer, and X-ray spectrometer, etc. So many things we mount on this beam line. And then we have something called cold target recoil ion momentum spectrometer, developed by our junior colleague in my group, and he has built a very, very world standard setup, and he's doing new experiments there, Dr. Mishra. So this is, of course, many of the beamline components I'm not going to explain. They're like optical components, focusing components. They're like focusing ion beam, steering the ion beam. They go away different directions, and we have to focus them back. So here is the real photographs of different experimental chamber. This is a electron spectroscopy chamber. This is X-ray spectroscopy chamber. And I have been building these kind of setups right from my PhD days here in TIFR. I did my PhD here before I went away for my postdoctoral research in Kansas many years back, of course. And now we have, of course, many collaborations and visits, different groups worldwide. But our main center is here in TIFR Mumbai. And we develop slowly all this is recoil ion momentum spectroscopy setups. All the setups we build in our central workshop in TIFR, which is a very, very sophisticated workshop. And you can get built a lot of your equipment because you know how to modify such equipment. Something goes bad. What you are seeing is X-ray detector here. And we have electron detector inside or recoil ion detectors all inside. And I will not go too much details. But here I just want to tell you, you see when charged particle goes into the body for your treatment, for applications, it loses energy. It loses energy. While losing energy, that energy loss, we plot here dEdx, means energy loss per unit distance. The energy loss depends on what is the energy of the beam. For example, if you fire a bullet with a very, very high speed, it will go through a glass window. It will not lose much of energy. But if the bullet energy is very small, like if it's coming to lower energy, if you throw a small stone, it's not much of energy, so it will not go through. It will not be enough, energy loss will not be there inside. But once it goes inside, it loses the energy and slows down. As it slows down, okay, then the energy loss, it happens, but energy loss also gradually loses more and more energy. So that's why the energy loss has a particular process. So depending on the beam energy, this is the initial beam energy. If initial beam energy is more, your energy loss goes through a peak. All of this. So this for proton, for example, on aluminum, it goes to a peak. Somewhere there is a peak. And after that, the energy loss is less and less because energy is so high, it cannot stop easily. And that is why this physics is very important for cancer therapy treatment in human body. I'll come to this. So for example, here, take a particle range. What I plotted before, if you have not followed, this is the energy of the beam. For example, proton beam. And here is a cross section, means what is the probability that certain energy loss will be there. So the initially lower the energy loss is more, higher the energy loss is less. And that happens for different projectiles. This is for hydrogen, this is helium, and so on. So we'll not go to these details now. Here is another example, the intensity. For example, many of you know, if you take a gamma ray, a particle gamma ray, photons, and alpha particle, and compare. If you take alpha particle, if it goes through the body, certain distance, it loses energy, but it does not lose the count. The I by I naught, initial intensity I naught and final intensity I, after passing through certain thickness here T, here is the source, here is the detector. How many are detected here? That is your I. I by I naught is almost constant up to certain distance. And where energy loss is very large, all the I by I naught comes to almost zero. Okay, so sudden transmission. Otherwise, the count was not different. But if you take a gamma ray, it follows this different curve. It's called exponential fall. I by I naught equal to e raised to minus mu t. T is the thickness. It exponentially goes down. This number of photon counts. So these two different behavior is very interesting. This is called Bragg's law. Next one, Bragg's curve. See, radiation therapy for cancer treatment. As I said, if you take a photon source like gamma rays, your intensity right in the beginning of the body, for example, suppose you have a body, very high intensity. Suppose my tumor is sitting at this distance. I hope you can see, at certain distance. If you want to remove this tumor at certain distance, you have to start with intensity which is very high in the beginning. Then only at the tumor, certain intensity will be there, and that is required, that intensity to remove the tumor. But if you go to alpha particles or protons, like charged particles, that this curve is different. You see, initially energy loss is less because energy is very high, the proton energy, as soon as it hits the body. But if you really go inside the body, your energy is losing. You are losing the energy. If you are losing the energy, then it becomes slow. If you slow, then they'll make you more slow easily. If you are slowing, then your energy loss increases. Because if you are slower, I'll tell you some of the physics concept later, it increases the various atomic physics cross sections, and that helps in losing more energy. So it becomes slows down, energy loss is increasing, and suddenly it stops. And this distance is called range, and this process is called Bragg peak, and so on. And so if you have a tumor here, you see initially you don't give much of dosage. Only at the tumor your energy loss is maximum, and that's all you want. So this is a kind of very nice technique to remove tumor. It's called Bragg's peak, Bragg's energy loss peak, and so on. So now I will not go to these details, except I am saying that what is the basic processes. One basic process, of course, is elastic collision to lose energy. Other processes are mostly inelastic process. For example, ionization. Ionization means removing one electron from the atom or molecule. Excitation, it can excite to higher excited states. Then it can also capture an electron from the target and goes away, the proton or carbon. And it can also not only single ionization, it can remove two electrons, double ionization. It can also happen both, that is ionization and capture together. You see the two electron process. So now this two electron process, of course, statistically, in general, at high energy collisions are much less compared to single collisions, single electron ionization, single electron capture, and so on. Typically 5%, 10% of that process. So many times people ignore such things. But without going to details, I can tell you the maximum energy loss, what happens in a, there are two processes. One is electronic energy loss and ionic energy loss, or nuclear regime, which is called energy loss. So typically the energy loss in a single electron for alpha particle is very less. In each case, only 1/500 of energy per nucleon. So it's not much at each step, but there are many electrons. So eventually you lose final electron energy because of the cumulative effect of the collisions with many of the electrons on its way. So here is an example of our instruments, what we use, like electron spectroscopy chamber. This is a high vacuum chamber which holds 10⁻⁸ torr vacuum. There is electron spectrometer inside here, which is shown here. This is hemispherical electrostatic analyzer. Now suppose the ion beams comes from electron beam, or ion beam comes here, collision happens, and electrons are detected by this hemispherical analyzer. So we apply a little bit voltage here, HV1 and HV2, depending on what energy electron I want to detect. And I keep changing this electron energy, and hence I keep changing the HV1, HV2 by scanning. And for that, of course, you have to use a computer. We have to use a proper data acquisition system, and all these are developed in my lab. And once you detect these electrons, we can detect how low, very low energy electrons, like 1 electron volt, 10 electron volt. These are lowest energy electrons, and these are very difficult to detect. Why? Because Earth's magnetic field or any electrostatic field inside the chamber, oil vapor, or any magnetic field will kill you. Okay, will kill these electrons. You cannot detect them. So that's why one has to be very careful how to handle this experimental setup. So you use something called mu metal sheets, to reduce the stray magnetic field. And vacuum is very good, 10⁻⁸ millibar or 10⁻⁸ torr. So now, as I said before, we use different highly charged ions, protons, helium, carbon 6+, oxygen 8+. But why highly charged ions and low velocity? Because in physics, those who are in physics, at least some of you know, that strong potential of interaction comes from large Q, large charge state. But lower velocity also is very good, because lower the velocity, longer the engagement time. So stronger interaction and longer engagement, that's all you want for any interaction, right? Even for human body. I mean, human, for example. You want stronger interaction and longer time, so to make a good friendship. Similarly, here also, to collide with ions, you need stronger Coulomb interactions and longer engagement, longer time, so lower velocity. So it demands a non-perturbative model because the perturbation strength is very large. Q by V is the perturbation strength, and Ecr Iron Accelerator satisfies both conditions. We can go high charge state Q and low velocity. Whereas in electron, I can still go high charge state but high velocity. I want high Q, low velocity, high perturbation, and that helps us for going to high perturbation strength. So theorists will be crying because they need to do a complicated theory, because most of the theorists use simple perturbative calculations. Okay, I give one example. 200 keV proton. If you take somebody does the calculation, you can do in home. Simple calculation. 200 keV. Just calculate the velocity for the proton. Velocity you can calculate in atomic unit, and you can also calculate 60 MeV carbon 6+. You see the again velocity. Of course, this velocity is much larger, but here charge state also much larger. Carbon is 6+, Q is 6. Here proton Q is how much? Only 1. Okay, so if you calculate for these two systems, you reach the same Q by V. But then the question comes, is the collision dynamics same? Now we have understood that no, it is not the same, although same Q by V. So now we just give an example which I told you before, more animation, that the charged particle coming here, it collides with the electron Coulomb interaction at large distance, and this electron will be emitted, and recoil ion to conserve momentum will come out, and the final projectile goes away. So I need to have a detector, I need to have a system to measure this final charge state here, these electrons, as well as this recoil ions. So I need several experimental setups, and each one is a big one, and it is not easy, let me tell you, for doing experiments. And then in addition, you also need to have the photon which comes out due to de-excitation of the states. For example, here it happens electrons, recoil ions, and now this is only for atomic hydrogen, which has only one electron. But life is not always in atomic hydrogen. You have to deal with complicated atoms like iron, gold. For example, here you see there is an atom I take which has many K shell, L shell, and M shell. This is called inner shell process, which I used to study many years back. Nowadays we don't do this much. Inner shell processes, and due to this inner shell process, you also can have a X-ray generation, X-ray spectrum. I am not going to details which X-ray spectrum and what physics I learned right now from this, but we published many years back in Physics later, in early days. And I will not go details, but what is the other process in the energy loss? So one process I showed, ionization. Other process is called electron capture. What is electron capture? Like this. So that ion comes, captures an electrons and goes away. So this ion is a positive ion, this captures a negative electron, and this charge state changes. Final projectile become neutral. Okay, so that way this target and projectile, this projectile and electron makes their planning beforehand. So that when the from projectile is coming, the friend is coming, they are talking to each other and they go away. They already planned it before. That means they have a lot of matching has to be done in their momentum space or binding energy and so on. Many parameters have to match to satisfy these conditions of electron capture. Okay, but there are different types of capture, which I am not going so details now. Another process for large energy loss. So one I said ionization, one is electron capture, and one is this is called giant dipole plasmon resonance. This is a collective excitation, because many times what I told you before is a single excitation. Their electron cloud behaves together, they oscillate together, they go to excited state and they decay by the electrons. It's like roadside, you see a lot of people, thousands of people joining together and doing some rally, michil. Okay, this is I want, that is I want. Okay, amader dabi mante hobe, this kind of thing. So there are collective behavior, this is a collective excitation. So it happens in physics also. Now, one example I wanted to give you here. What is that example? This is a example of different process. What is their cross section? What is cross section means? Cross section means in this case collision probability, something to happen. What is the probability? For example, in this case electron capture probability is a charge transfer, proton on helium target. What is the probability? Now you don't have to understand everything. Just see one of the plot that this 0 to 1, 0, 1. This is like, for example, ionization process, and this is the energy of the ion beam. So this energy, you look at the numbers, 10⁴ to 10⁵ electron volt. That is exactly the energy of ECR ion beam from the ECR ion source. So they are like 10 kV to 100 kV. And you see, all this process has a peak in this region. That means it's a very strong process at this medium energy or intermediate energy, we say. Because why these peaks happen? Because at this energy, projectile comes with a velocity which roughly matches with the electron orbital velocity in the target. So it spends enough time to excite or to talk to the target atom. So that is why this process, all processes are like higher cross section. But if you go higher energy, look at this. The ionization cross section goes down, but not so drastically. But this dashed line is a capture cross section, electron capture. Goes down very, very fast. So this velocity dependence is just velocity. This velocity dependence is v raised to minus roughly 11. Okay, this is, or minus 12. That means velocity increases, cross section goes down at v raised to minus 11. Where ionization cross section goes as 1 by log over E, v square. V square log E means v square is E. So 1 upon energy, but or 1 upon v square, whereas this is 1 upon v raised to 11. So that's why when you go to electron energy, we are in this region, where cross section is still there, but goes down compared to the ECR energy range. So that's a nice place to study. So I'll just give an example of an electron capture, electron ionization, how a spectrum looks like in an electron spectroscopy chamber. So a spectrum looks like a bit boring because it's a continuum spectrum. What does it mean? This is the target is water molecule. Projectile is oxygen 8+ at very high velocity, like 10 times velocity of electron. So energy is something like 4.5 multiplied by 16 is the mass for oxygen. So whatever. Okay, so 4.5 MeV per U, that is the energy. So 72 MeV oxygen or something, this one. And you see theoretical cross sections calculation by perturbative calculation, it's called CDW, continuum distorted wave calculations. I'm not going that details, technical details here. Gives a reasonably good agreement with the overall spectrum. But what is interesting to see here, the spectrum falls. Higher the ejected energy, what I'm plotting here is not written here, it is written in this plot, ejected electron energy. Ejected electron energy, what is electron coming up in a continuum? So higher the continuum energy, lower the population, lower their population, lower energy, lower cross sections, very lower. And this is called KLLOJ, characteristic of oxygen in water target. And another thing you have to remember, this is one more example of neon. This is for water. So you see cross section falls by 3 to 4 orders of magnitude. That's why I had to plot in log scale. Now, if you take any one particular energy here, and I plot, for example, 100 electrons, or sit here and take their angular distribution. Because my detector, I can change the angle also. And you see, it goes to a peak around 80 degrees or so. So this is very characteristic, ion atom collision, very fast collision. Momentum is transferred only to the transverse direction. Okay, transverse direction. And that's why the peak comes more or less around 80, 90. These are the only two things you have to remember. This is a monotonous peak, and the peak comes around 80 degrees. That's all you have to remember. Nothing else, rest of the talk. Now I give you, is it boring? This is for water, this is for neon and simple atom. What happens in case of hydrogen molecule, which has 2 electrons? Hydrogen molecules. See, there's very interesting thing happens. Hydrogen molecule has 2 electrons. These 2 electrons can behave as an independent scatterer. And if that is so, like a double slit experiment, you know, in a double slit experiment, Young's double slit experiment, light is scattered and you see a fringe. There is a probability of constructive interference and destructive interference. So this is also, can it happen in case of electron beam? That means electron scattering from a molecule, because molecules, if you want to do the same experiment, if you look into the energy of the electron are keV energy, whereas light energies are EV, about 1 EV or so. So 3 orders of magnitude larger energy here. Hence, de Broglie wavelength also will be much smaller. Lambda. Okay. And if you calculate the de Broglie wavelength for 1 keV electron beam energy, the de Broglie wavelength becomes, all of you know, about an angstrom. You can calculate. So that means I need a double slit of distance 1 angstrom. But where can I get a double slit of 1 angstrom? I cannot buy from market. So what do? You basically think there's a Cohen and Fano many years back suggested, can we use a molecule as a scatterer? Molecule has 2 atoms separated by a distance d, which is about 1 angstrom. And that is the idea we have been working last decade, and we have several, I should say, pioneering results came out from our lab on this topic. So one way of doing this, as I said before, the experiment, actually the spectrum is very boring, monotonically falling. But can there be masala? Can there be spice? So it can be more interesting. Tok, jhal, taste. Kichu ana jete pare? That is the point. Now you see tok, jhal, taste. So this was published again several years back, and in another physics later. And you see, this is the oscillation you see in the electron spectrum. And this oscillation was not there in the previous spectrum, which I showed you. So this is the beauty, and this is the theory. Red line is a Cohen-Fano model, which assumes the interference and fits. Okay, but then of course we did ab initio calculation, which also reproduces such oscillatory behavior in electron spectrum, as if somewhere there's a constructive and somewhere there's a destructive evidence. Okay, so this is coming from the molecular hydrogen oscillatory behavior. Now, what details, technical details, I'm not going, how we are doing and so on. Then the question comes, okay, molecular hydrogen is a diatomic molecule, simplest diatomic molecule, 2 identical atoms, but can I have another molecule? For example, nitrogen and oxygen. They are also homonuclear diatomic molecule. If that is so, then I should be able to see that also in the electron spectrum. But do we see that? That is the question. Just 1 second, please. Okay, so this is the example. I just want to give the final results only. It is on the latest, just 2 years back or 3 years back, we have studied this. This is, again, you can see nice oscillatory behavior in the forward-backward asymmetry parameter or electron spectrum. Basically, try to understand from electron spectrum. This is on electron collision on nitrogen. And we could really see this oscillatory behavior in oxygen and nitrogen. So that proves that, yes, this is a double slit type of behavior. So molecules can be used in nanoscopic, nanoscale double slit. One more example. Now I put all 3 here, not only from our group but others. So here is the data from photoionization. That means nitrogen and oxygen. Again, this for oxygen. In photoionization experiment, it was done in Besi in Berlin. So in a collaboration, I did this studies there in the group of Professor Uwe Baker, and it was a very nice oscillatory behavior could be seen. It's a state selective oscillation, very nicely observed. Then we did this experiment here in Mumbai with heavy ions like carbon ions. Unfortunately, we could not see this oscillation in carbon ions. So we got surprised. What happens? Charged particle doesn't show these oscillations where we do see in hydrogen, molecular hydrogen. But we did not see that for molecular oxygen or even nitrogen. So then the question comes, can I do this in a tabletop experiment of nitrogen? You don't need an accelerator. একটা টেবিলের উপরে ইলেকট্রন বিম সেট করেও এই এক্সপেরিমেন্ট করা যায়। তো আমাদের ইলেকট্রন বিম আছে, ইলেকট্রন বিম গান আছে, কেভি এনার্জি ইলেকট্রন গান আছে, and we set it up, this experiment, our students, and this experiment was done, and you could really see, yes, we could see very nice oscillatory behavior. So there's some technical reason why we don't see heavy ions, because of some cancellation effect of certain. I can explain later if there is there. So now I come back to the Bragg peak again. As I said, now I go to a little more complicated molecule. Take the Bragg peak example I gave you before. I repeat it again. Those who have not followed last time, now we can repeat. See this plot. x-axis, I am plotting depth. That means a charged particle like carbon ions going inside. Very high energy. How much energy? 200 into A. A is 12. 12 into 200. That means 2400 MeV, 2.4 GeV. And this is 4.8 GeV. Very high energy carbon. It goes inside your body. Is a water. This calculation for water, that is because in the body most of it is a water. 60% or more is water. So here it goes up to 25 centimeter or 30 centimeter. Here this energy it goes little less because it's half the energy. Here it goes something like 50, 60 centimeters, something like that. 50 millimeter, 5 to 6, 7 centimeter. Whereas this 25 and so on centimeter, something like that. So huge distance it can go. So if you have a tumor in this region, it can remove. If you have a tumor here, this is called Bragg peak, as I said before. If tumor falls in the Bragg peak, you can remove. So the doctors beforehand know what is the location of this tumor, and physicists calculate what will be the energy loss, and then they collaborate, and that's why you need to do this study. So here is the real life example. Again, if you take a gamma source, it will not only destroy your tumor or cancer, it will still go through and removes a lot of other cells also. Whereas in case of heavy ions like carbon ions, it will remove only the tumor. Side effect is much less. So now what is the basic physics? People have understood now. A science paper in 2000 that shows that low energy electrons are the culprit. They are the basically responsible. These 3 to 20 eV or 30 eV lowest energy electrons are responsible for radiation damage. Okay, so in our heavy ion collisions, as I showed in the previous spectrum, we produce a lot of low energy electrons here. Lowest energy electrons, highest cross sections. So question is how much this low energy electron can produce, and these low energy electrons will go in a chain reaction, and will destroy the other cells which we want to destroy. So here is, of course, is that many of you know the ATGC, okay, adenine, thymine, and guanine, cytosine, and these are the building block of these the base molecules of the DNA and so on. And of course, in RNA we also have uracil. So we take any example, any one example, and we study their ionization process. So one example I give you here. So this is another equipment in which electron gives a start signal, and ions which is produced, they give a stop signal here. Ions come slow, and this is called time of flight spectroscopy. This is a pusher. You apply a voltage here, another voltage here, another voltage here. Of course, this is oversimplified. We do much more complicated recoil ion momentum spectroscopy nowadays. And electrons are attracted this way, ions are attracted this way because their polarity is opposite in the voltage. And you produce something called time of flight spectroscopy. And from time of flight of this motion, we can find out what is the mass by charge ratio, M by Q. So we can separate out different mass by charge ratio. Again, without going to details, I just give you one example of one result. For example, you take a uracil molecule and calculate what is the total ionization cross section. Okay, so now I think I take hopefully I can take some more time. So now I am coming to this example of uracil, and this is I am plotting as a function of energy. Okay, energy per atomic mass unit, and this for carbon ions. This is 1 means carbon ions atomic mass unit, 1 means 1 MeV per U. That means 12 MeV is the total energy. This one is this. Okay, where carbon has 12 MeV is the mass. So go to higher energy. This is the electron data, high energy, 12 MeV to something like 60 MeV, 70 MeV energy here. And you can see the data falls very fast, cross section falls very fast. But if you go to lower energy, it increases. And this is the energy which is Ecr Iron Accelerator, my Ecr ion source. So here, this is the first set of ever data, which is absolute cross sections. And this is very useful for doctors, for input, for modeling. radiation damage. And what is one needs to know total absolute probability. And that's all we are putting here, total absolute probability or total cross sections. Now you can ask the question, does it agree with some theory? Here's a red line is the best known theory. It's called CDWEIS. Without technical details, I can tell you just factor of 2 high, this theory tells. Whereas you go to lowest energy range, where the peak is there, it's almost factor of 5 high. So that means theory fails to reproduce. So hospital doctors will use this theory in absence of experimental data. So here we showed that you need absolute measurement. Otherwise, people will do mistake. You will give wrong doses maybe to the patient, and he might suffer more, or she might suffer more. So here is another example. Now look at once our data was published, it is very interesting. Within 6 months or so, we could see another publication in which they picked up our data and they could reproduce here this right side plot, our data with this red line, dashed line. You see, it goes very well with our high energy as well as low energy data. The theory goes over it. So what does it do? What was missing in the previous calculation? This is missing. You see, as I told you before, not only ionization happened. This paper by Montenegro from Brazil, and they did these calculations for our data, and they picked up our data. And it's very nice that when you do publish some results, somebody else picks up somewhere in the world. And that's why science is universal. You do something, you publish it, it is very fairly transparent, and you publish the correct data. Otherwise, you'll confuse other people. Okay, as much accurate as possible. So here is the ionization process and electron transfer process. I told you, from target to projectile, electron can transfer. So both can give energy loss. But can then happen together? Yes. At the Ecr energy range, because the energy is low, there is a good chance that this both process, two electron process, is comparable. And when you add this mechanism in the theory, they get a good agreement. You see this line, very good agreement, this solid line. So now this is another example I give you. Now you can ask me a question. Okay, the low energy electrons which causes the damage. Fine, very good. How can I increase the low energy electron emission probability inside the tumor when we have the collisions? So there is a proposal. There is a proposal that if you put a nanoparticle, so it's a marriage between nanotechnology and radiobiology. Put a nanoparticle inside the DNA and RNA, whatever. And if you put a nanoparticle, let the charged particle go through this. And if it collides with this nanoparticle, that has a lot of electrons. What is this nanoparticle made of? Gold or silver, some metal. And these metals have a lot of loosely bound electrons. And this large number of electrons can be emitted, and these electrons will further collide with the adjacent water molecules or other molecules and produce lots of electrons or radicals. So you see, there is internal amplification of electron production, not by increasing the dosage. Dosage is the same, just by putting in a nanoparticle. So this way, I can reduce the dosage, but still I can increase the number of electrons. But does it really work? We wanted to do an experiment, and we did an experiment. Take a simple molecule like uracil and replace one of the hydrogen by iodine, I or bromine. This is called halouracils. Once we put iodine molecule, iodine atom, what happens? This is an experiment, we did it. But before I go to details and result, I must tell you these experiments are done, these biomolecules or C60 Fullerene. How do I do an experiment? They come in a powder form. And we heat them, and you make a vapor, hot vapor, and let the ion beam goes through that vapor. So the vapor is very thin. It's a 1 or 2 millimeter, some kind of diameter of that any particular cross section, and ion beam passes through, which is of the order of millimeter, and then you should have a perfect alignment. Otherwise, you'll miss the target atoms. So these experiments at times very difficult. You have to finish entire experiment in one beam time, which is about 5 days or something in Electron Accelerator. But ECR, it is a nice thing because our own accelerator, so we can do these experiments very well, taking enough time. And this is the typically vapor source, water cooled and so on. And we also have a thickness monitor. We measure the vapor flow of vapor. We measure, we can also measure actual thickness, what is deposited on that. So it's called quartz crystal thickness monitor. So this we develop our workshops and do these experiments. Now, just come an example, one results. When I told you that I put iodouracil and uracil, so I compare their experimental results. So here is the results. Now you can, again, do not get into too much. Just try to understand what I am plotting. One of the plots. X-axis I am plotting angular distributions. That means angles. This is angular distribution. Angle of electron emission. As I explained to you before, you remember, there is a peak kind of behavior around 80 degree. So, which is there in each case. And what the two plots are there? The black circles and red triangles. What does a red triangle means? Uracil data. Data coming out simple, one uracil. Electron number, whatever number of electrons coming out. And the circles are bromouracil, iodouracil. Means it has one iodine attached. One hydrogen is replaced and one iodine is attached. You see the cross sections have gone up, probability has gone up everywhere. Everywhere is gone up. Okay, each plot, that this is 20, 21 electron volt, 40 electron volt, 100 electron volt, and 180 electron volt. Each electron energy, the number has gone up. And how much gone up? And what is the line? Line is the theoretical predictions. So the difference between in experiment to experiment, with uracil to bromouracil, is much more compared to theoretical difference. The dashed line and solid line, not much of difference. I'll come to this again as a ratio. So now here I plot the ratio. Forget about this left side plot, just concentrate on the right side plot. You look at the ratio between iodouracil and uracil. If I put iodine and if I don't put iodine, you may ask a question, why iodine? I am coming to this. First, you look into these results for 2 minutes. That means you see the results. Number is very important in experiments and particularly in physics. Numbers are very important. So here the ratio comes how much important? Between 2 and 3. Here also between 2 and 3. Here also 180 electron volt between 2. This is the 2 and 3. So the ratio is increased by a factor of 2 to 3, basically 2.5. These are different angles here. 45 degrees, 60 degree, 135 degree, and backward angle 120 degree. Each case you see the ratio is nearly 3 or between 2 and 3 and so on. So 2 to 2.5 times average enhancement in electron emission over uracil. But why is this enhancement? How much you expect? And why iodine? See, iodine is used because iodine, xenon, these are 4D electrons, 4D shells are filled. Okay, and these are known to have a, see, xenon is 54 atomic number and 53 is iodine and so on. So these 4D electrons have a collective state. It is very well known. This is called giant dipole resonance. Atomic giant dipole resonance. Now, giant resonance, plasmon excitations, these are known in condensed matter physics as well as nuclear physics, giant dipole resonance. But in atomic physics, also in case of xenon, one knows GDR, giant dipole resonance. But iodine also is known, simple iodine. Question is that we get different ideas and give a marriage. Put an iodine in the uracil. And if you increase this electron enhancement because of the collective excitation and then decay the state, these electrons can be used for radiobiological other chain reaction processes, which can help more damage. That's all you want. And this is a very important, interesting paper. We tried to submit this paper to PhysRev later, and we fought for a long time, last more than 6 months or so. But even other some high-profile journals. But finally, we agreed to publish it. Physical Review A. It is just accepted just a week back, and it's coming up this paper. So now, question is that that means what is happening? The idea is more than 2 times we see enhancement. But do we expect this 2-time enhancement from theory? No. Is it theoretical enhancement is only 1.1, that 10%, 1.1 type, 1.2 type at the most, like 1.0, 1.05 times. So basically within 10% enhancement is understandable, but we are getting a factor of 2.5, which is very large, dramatic enhancement. That means this much enhancement will cause your doses can be reduced by this much, and electron enhancement will be large, and that's all we want. So we predicted that this can be used as a nano sensitizer. This is called nano sensitizing effect due to the plasmon excitation. In this case, we say due to giant resonance. Our proposal by Solovyev's paper in 2015 in PRL, his group, they said yes, plasmon excitation can cause such enhancement. So it is in this direction we found just one iodine can help to give you 2.5 times enhancement. Another question is, okay, these are the same results I'm showing, this enhancement of 2 to 3 times. This is due to the atomic giant resonance. Now, putting a nanoparticle, there's only one experiment so far has been done. They have seen the enhancement happens typically 1.8 or 2 times around that. But there's a large number of nanoparticles, 1,000 nanoparticles together in a cluster, putting in a DNA really. And these experiments are very, very challenging. It's very difficult to do such experiments, and it is not easy to understand. Now I come a little bit again basic physics and just a few more. So basically I finished roughly 1 hour now. So I can take little more time, Dr. Pretam.
Yes, sir, you can.
I hope people are understanding, the students. I am going slow. Even my normal skill compared to that, I am also slow. And so far, just summarize to you, what I have talked, not much. I have talked basically, if you look into the example, one example was molecular hydrogen, and I said the molecular hydrogen can be used as a double slit, which is important, fundamental for fundamental quantum mechanical experiments of interference by electron wave, because electron is also a wave. So to see this effect in a single double slit, it is very difficult technologically. So idea was to use a molecule. So molecular hydrogen, then we use molecular nitrogen and oxygen. Now I'll tell you, this topic is very interesting, and all over the world, many groups are involved in this. Of course, there are many experiments have been done, starting from the initial work of Nico Stolterfort in Meitner Institute, Germany, and then followed by several experiments, John Tannis's group, and recently some other molecules, and using different techniques. This is a very interesting topic. Now question is, comes to the biomolecules, and I said that biomolecules, if you do not include a double electron process, 2 electron process, like ionization plus electron capture, you do not agree with the theory. The experiment provides much lesser cross-section of probability compared to theory. But the moment you added the 2 electron process, you get much better agreement. Then in addition, I showed the third thing is, if you add a nanoparticle, in our case, a simple atom, if you attach a DNA or RNA based molecule, for example, uracil in RNA based molecule, in this case, you could see that yes, you could enhance the electron emission very large by factor of 2.5, which is large. And this has technological applications in near future, hopefully. Now I am just giving an example. Take another example. We have Ecr ion source in which we have a 200 keV proton data, and take the electron experiment where 66 MeV carbon data. As I told you in the beginning, both these cases, if you calculate the charge state and velocity and take the ratio, you will get same, almost same. So these are the 2 collision system. Here is left side is 200 keV proton collision, and this is on 66 MeV carbon 6+, and both case target is oxygen molecule. You see the electron energy distribution, angular distributions of the electron emission. You see steadily growing down, steadily low cross sections. Going from lowest angle is the highest cross section, and it is not going to a peak, like as I told you before, 80 degree, we see a peak here. Here also. You see the low energy electrons goes through some kind of steadily decreasing cross section. That is because it is so low energy, the perturbation is so strong, the electrons are directly influenced by the projectile motion. It is attracted towards the forward direction, maximum. That does not happen at this high, very high energy, like 66 MeV. Second thing is another example, of course, backward angle. 40 electron volt, high energy, and all angles, backward angles as well as forward angles. And again, you see the higher energy, higher energy beam has a completely different distributions compared to the low energy beam. Here, asymmetry is very large, electron asymmetry. That means forward angle has much larger cross section than backward angle. So the forward divided by backward is called forward-backward asymmetry. Here the asymmetry is very large, and here asymmetry is much low. Although both cases we have same Q by V, so only one parameter Q by V does not give the similar distribution. That is an interesting finding according to me. From my experience in this field from many years, we had a very different idea. So initially. So this, and of course you can see theory also does not agree so well in the ECR energy range, whereas that agrees quite well in the electron energy range. This is a very nice example, like a textbook kind of example we have got and published just recently. Again, these are all lockdown paper during lockdown. Now I give you another example of water molecule, which is very, very important. And this is not our paper, somebody else's paper, Ron Olson's paper, and Olson published in 2019. I got to know their paper. I found in this paper, they have put many data, and all these triangles data here, all this data I found out taken from our paper. So our all water paper, which I did not talk today, lot of demand internationally, and many people use this data to validate their theory. So here is the theoretical model, scaling law, this dotted black dots. Now recently, we did these measurements again at the low energy, ECR energy region, and you see we get an excellent agreement with the new calculations, CTMC, Classical Trajectory Monte Carlo. I have not yet published these results. So this will come in this plot here, because this is the entire energy, low energy to high energy. This plot will come here. We have to see how it matches. So this is so far. This now I give I skip some of them because no point in giving all examples today. I give you one more example just on electron spectroscopy only. You see very surprising results. Now I say, as I told you, the coronin is a molecule like here. Coronin is C24H12. C24, what is this important? These molecules are called PAH, polycyclic aromatic hydrocarbon molecules. I think I have a slide here. These are all planar molecules. They are abundant in interstellar medium, almost 10% of the carbon, total carbon in the universe. And these are most abundant polyatomic species in the interstellar medium. These are called polycyclic aromatic hydrocarbon molecules. And these are delocalized pi electrons, highly correlated, and they show collective excitation. That is why my interest, as well as those photonics people, UV photonics or VUV photonics in condensed matter physics also have some applications of these molecules. So the interaction with various interstellar medium, the radiations from there are ions, electrons, and photons. They interact with these molecules. Okay, and then we study, that is why fragmentation upon interactions with the radiations, also the ionization, electron emission, everything we studied. And we have published several papers on this already. And now very recently we've got some new measurements. We are trying to look for collective plasmon excitation behavior in coronin. Coronin is this molecule in which many carbon atoms together, and these electrons, the sigma and pi electrons oscillate together, and they are very strongly correlated systems. And another molecule is fluorine. You see, coronin is bigger molecule. It has 24 carbon atom. Fluorine has 13 carbon atom. We are doing a comparative study between the two, how the collective plasmon excitation behaves. So forget these slides. Now come back to this. Coronin shows very clearly when you plot the electron spectrum. Here is the energy of the electron, and here is the forward by backward ratio. Okay. And this you can see clearly in case of coronin, it goes to a peak. These red points as a function of ejected electron energy. And that happens right at the energy where we expect. Okay. And this is around 21 electron volt. This thing happened, this peak, and minus ionization potential. So this thing together, this peak comes around 17 electron volt and so on. And you may ask me a question, what are the other two? The other two are, one is methane and one is neon. They are usual molecules and they do not have any such peaking behavior. This was very interesting. And we again tried to publish in PhysRev later, but we succeeded in publishing the rapid communication in PhysRev A as well as scientific report a few years back. And you see, this is the theoretical calculation showing a plasmon type behavior, collective excitation behavior, plasmon approximation. And that matches very well at 17 electron volt. Now you may ask a question, is this the only thing? No, there is a classic behavior that was almost toward the end of the talk. I studied many years C60 Fullerene. That is our benchmark study from our group, and very, very well known this study. C60 Fullerene, you look into the C60. C60, as I told you before also, 60 carbon atoms, 60 into 4, 240 electrons, which are valence electrons. And these electrons, they both sigma and pi electrons, they collectively excited. And then the finally decays by an electron emission. Then I should see a peak around that excitation energy, whatever 20 electron volt is the excitation energy. I should see a peak at around 20 electron volt minus ionization potential, because you have to, this system is decaying by electron emission. So what is the original binding energy you have to subtract? So you should expect a peak around 10 or 12 electron volt, and we do see a nice behavior. You see the peak in this region. And if you did not have this, you just take a simple atom like neon, you see this red line. There's also multi-electron system and there is no peaking behavior. It's very clear plasmon peak. This is the first time, I think, how the plasmon electrons are detected. These are the first ever measurements. And then we found, of course, TD DFT calculation agrees very well. After our publication, we could see a good agreement with the calculation here, and they agrees very well with the plasmon excitation. So now I think I will not give more examples on that. I just wanted to tell you that one more news, EPJ news page, you got an email, I think August it is. The very nice, we are pleased to inform you that a synopsis of your article, Electron Emission in Ionization of Adenine Molecule, is available on the EPJ news page. So it has been accepted as a highlight or news, which is very pleasing information for us on this biomolecular work. So basically what I have tried to talk to you, basically interference mechanism, electron transfer mechanism, little bit of fragmentation of different of C60 Fullerene or uracil biomolecule, and wanted to hint you on the many electron correlations and collective excitations called giant resonance, and there's plasmon excitations, and large scale instrumentation building is a part of our work. Otherwise, we could not have done this work. In fact, there are many results I have not shown. It's not the idea to show you all results here. I am going slow and trying to explain you certain concepts, because this is not known to many people, because this is more like interdisciplinary science, and not only just pure atomic physics or just molecular scattering, but in the application of atomic and molecular scattering in different related fields, like astrophysics related field through pH molecules, or biological applications like radiation damage of uracil, or nano applications for the radiobiology, nanoscopic applications, nanotechnology, so that you can use something called nanosensitizing effect, which has a very good future implication to cancer therapy. Now, these large-scale instruments are building Ecr Iron Accelerator, X-ray spectroscopy, electron spectroscopy, recoil and momentum spectroscopy. We also have a VUV monochromator. We also have electron beam gun setup, and we have our group, very strong group, which helps to do all these things, and accelerators and ion sources. So this is, so far my comments and outlooks are like development of ECR ion source in TIFR, which has given us an edge, not only using high energy accelerator, but low energy accelerators. People are welcome to write to us and use our machines. No committee here. Of course, for Electron, if you have a committee, even there I am there. Electron Accelerator, we have a implementation committee, which again I look after that committee also. And electron emission from double differential and total cross sections for several biomolecules, nanosolvated biomolecules, like I gave you an example of ioduracil, and pH molecules and so on. But my final comment will be, as I was telling just 2 weeks back, I had a national seminar here, one webinar, I made the same comment. The realistic measurement of total energy loss in the matter is required. and for which we need to know actual cross sections of ionization, electron capture, particularly in the Ecr energy range, which is not known at all. So there are a lot of scope to grow in this field in many places and worldwide. So this is one more example I have to give you. This is a review article which is just published in 1 or 2 years back. I think this I told you before, in Singapore, World Scientific and so on. And one topical review I'm going to write. Hopefully I'll write. Invitation is still there, but it is taking time. So I have a pleasure to acknowledge my colleagues, Dipankar Mishra, who is my, in my lab, and he is developing new setups and doing lot of new experiments. Then I have a very good technical and scientific staff which helps us maintaining experiments, labs, equipments, and so on, writing softwares. Mr. Fernandez, Mr. Tulasiram, Mr. Pathare, Nilesh, Manjrekar, and Raman. And also I have several PhD students. In recent days are Chandan, Siddiqui working directly with Dipankar and doing a lot of work in using ECR. Okay, then Abhijit, Himani are my postdocs, and Soumitra was another JRF student, and Madhusri there was another JRF and SIF student. So these are the recent students who are finishing their PhD, and past members of Samik and there are many. You see, many of them are in France or IIT Delhi, IIT Kanpur, IIST Trivandrum, then UK and Mumbai University. They are faculty members in different places now already. And past member, many of the postdocs are different members in the institute, in different institutes in TIFR, many of them actually. So many students and postdocs have gone through my group. And I also have lucky to have a good theoretical support. Roberto Rivarola, long-standing collaborations from Argentina, Tapan Mukherjee, PK Mukherjee from Calcutta, along with Jayanta Saha and others. And Chapo is from France, Pablo is from Brazil, and Argentina, and Sarkadi. So I have collaboration both Brazil and Argentina, and Gulias from Hungary, and so on, Santos from Portugal. And so we have we have fantastic central workshop and several project students. So I thank all of them. So I think I must thank you for your patience for listening this talk. This is TIFR Seashore, as I write, as Jhorer Prate instead of Rate, Jai Hook. Seashore is the stormy day. Even Tata Institute or many research institutes, actually we have stormy days many times, because we are always kind of kept, all the time you have to have a nice results, nice reviews, funding, and you have to prove yourself all the time. So life is as stormy as these days. So I think I should thank you very much.
Thank you, sir, for your wonderful presentation, sir. So if you allow, we can start discussion session, sir. So we have got one question from our guest from Philippines. So I can read the question. So how many processes are involved in harvesting this energy using different targets?
How many processes?
Yeah, how many processes are involved in the harvesting this energy using different targets?
Okay, actually, large number of processes. There is no one process. As I said, elastic scattering is one process. Ionization is another process. These are the major process, and fragmentation. Then comes single ionization, double ionization, and as I showed, ionization and transfer together. It also depends on what is the beam energy. At certain energy, certain processes are very strong. For example, if you go to very high energy, electron capture process is very low. Very, very low. You can ignore simply. But if you go to ECR energy, lower energy range, like 10 kV, 20 kV, 100 kV energy range, you have to take ionization, electron transfer, or even double electron processes almost on the same footing. And also it depends on the target. For example, if you take a hydrogen target, simple neon target, certain things happens. But if you take a complicated molecule like uracil or C60, you have to assume many other processes.
Thank you, sir. We have another question, sir. Which method is safer in cancer treatment, radiation therapy, or nanotechnology?
Now, okay, I must tell you first of all that I am not in the field of radiobiology, or I am not a doctor. So I'll not make a concrete comment. But however, I want to tell you that nanotechnology has many techniques, which we are not doing here. We are doing only radiobiology, in which a uracil or a biomolecule or a body or a tumor, in which you can insert a nanoparticle and do collision experiments. So if you do collision aspect, then the nanotechnology, of course, has a edge, it wins over just without nanoparticle, but it has to be actually experimentally seen properly. It is still under investigation. But other nanotechniques and so on, of course, I will not comment on that. But radiation biology using high energy ion beams is a very, very, I should say, very fruitful technique worldwide at large accelerator center. You need GeV energy beams.
Thank you, sir. We have got one question in inbox also. So one student want to know that in Linux we see that 6 MB or 15 MB Linux linear accelerator. So what is the difference between MV and MEV?
Okay, MB and MV. That's a good question. I'm stopped sharing. Okay, I'm stopping sharing.
Yeah.
Okay.
Okay.
So the question is, that's a good question. See, MV is the potential what you raise. Like a terminal voltage I put, or my acceleration I put on a voltage, how much voltage, that is MV. But if you charge particle, you accelerate using that energy, then it becomes MEV. For example, if you take an electron, one electron, or one charge state or proton or whatever, if you accelerate to a certain 1 MV potential, then energy of the electron will be 1 MV multiplied by 1 electronic charge. So 1 MeV. So MEV and MV is basically charge multiplied by the potential. And other one, MV is just simply the potential.
Thank you, sir. As we don't have any more questions, so we can conclude our discussion, sir. Thanks for accepting our invitation, sir. We'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology. Sir, we have organized this webinar to encourage our students in this corona pandemic situation. So you have accepted our invitation, though you are too busy, as you mentioned in your lecture that in this pandemic, so you have already published several papers. So we know that you are too busy with your works, and you still give us time. So thanks for accepting our invitations, and hopefully in near future we'll arrange another webinar with you if you have time, sir. So thanks again, sir.
Always welcome. And it was a pleasure for me, as I told you, যে তোমাদেরকে বা আরো যারা আছেন তাদেরকে এই টকটা দিতে পারার জন্য, মানে
আমাদের জন্য অনেক ভালো লাগে স্যার, আপনাকে আমরা আমাদের মাঝে পেয়েছি, এবং ভবিষ্যতে অবশ্যই আমরা সামনাসামনি পরবর্তী সময় অবশ্যই আমরা যেহেতু পাশাপাশি কল্যাণী আর পাবনা 200 কিলোমিটার, অবশ্যই স্যার আমরা সামনাসামনি একটা টকের আয়োজন করব করোনা পরবর্তী পৃথিবীতে। অবশ্যই স্যার, তো ভালো থাকবেন স্যার, সুস্থ থাকবেন, এবং এভাবেই আমাদের মাঝে আপনার জ্ঞান বিতরণ করে যাবেন স্যার।
ওকে, থ্যাংক ইউ সো মাচ, নো প্রবলেম, মোস্ট ওয়েলকাম।
ভালো থাকবেন।